All right. So we want to look at velocity graphs in one dimension and try to figure out what's going on. So this is something I actually wrote a program to create this graph, but you could do all sorts of things. So here I have the velocity in the x direction. You can't really graph the vector velocity. You can only graph it in one direction versus time for some object. Let's say it's a car on a track. Actually, it'd be pretty big because this is pretty fast. So it starts off here. It has x velocity of 10 meters per second, and it's constant until the time of 8 seconds. And I don't know what happened. I don't know why this line should be right there. It just printed weird. There's something wrong with the thing. But I wrote it up here. So it's at a time of 8 seconds, and the velocity is 10 meters per second. And then the velocity decreases down to here up until a time of 14 seconds where the velocity is negative 11 meters per second. And then it travels on until 20 seconds. So during this whole time interval, how far did it go? Well, we can break this into 3 different parts. So we have this part 1. We'll call this delta x1. And then we have part 2, delta x2, and then we have part 3, delta x3. So I can find out how far it went during this part, how far it went during this part, and how far it went during this part, and add them all up. And then that will tell me the total distance traveled. And I actually did print out the position versus time graph so we can compare that at the end. So let's start with this first one where I have the objects moving at a constant x velocity. So in that case, let's just switch over to a piece of paper so that I can have more room to move. I don't want to mess up the graph too much. Okay, so I know the definition of the average velocity is the change in x over the change in time. Okay, if you write v equals d over t or v equals x over t, don't do that. Don't do that. No. Don't do that. Okay, that's not true. That may give you the right answer in some cases, but there are a lot of cases where that will not give you the right answer. So just don't even do it. Don't even think about it. Okay. So in this case, you'll notice here that I have delta x. I don't know what the starting position is. So I can't get that from the velocity graph. So I can either pick a value or I'm just going to solve for delta x. So in this first case, I know v1 is equal to 10 meters per second. And delta t1 is equal to 8 seconds. So up here, I can solve. The average velocity is the velocity. It doesn't change. So this is v average. So now I can solve for delta x. Delta x1 is going to be v1 delta t1. So it's going to be 10 meters per second times 8 seconds equals 80 meters. And you'll notice that the units do matter, right? Because here I have meters per second times seconds, and the seconds cancel and I get meters. You can't just use whatever units they give because it might not make sense. If I had miles per hour and seconds, they're not going to cancel. Okay, so you have to make sure that everything's in the right units. I'm not going to really go into a lot of crazy unit problems right now. I'll give you an example, but just so you know what that's going on. Okay, so that's delta x1. Now let's go back to the next part. What about x2? Here it starts at 10 meters per second and ends up at a negative 11 meters per second, and the change in time is 6 seconds. Okay, so let's just write that down again. Start from the same principle. So v1 is 10. v2 is negative 11. Delta t2 is 6 seconds. So in this case, I can use the exact same expression. You could say, well, what's the acceleration? And we'll talk about that in a second. But if I use v average, it doesn't matter. I can say v average is v1 plus v2 over 2. That's how, if the acceleration is constant, if it's changing at a constant rate, then I can do this. I can just add the initial and the final velocity, and divide by 2, and I get the average velocity. So this is going to be 10 plus negative 11 over 2, or negative 1/2 meters per second. And I can say that's equal to delta x2 over delta t2. So delta x2 is going to be equal to negative 1/2 meters per second times delta t2 of 6 seconds. and that's going to be negative 3 meters. Okay, so now we just need to do the last part, which is, again, a constant velocity of negative 11 meters per second for a time interval of 6 seconds again. So I'm going to say V average equals V3 equals delta x3 over delta t3. So delta x3 is going to be V3 delta t3. So it's going to be negative 11. I'll leave off the units just for space, and 6. So I get negative 66 meters. So now my total delta x is going to be 80 minus 3 minus 66. So that's negative, that's minus 69. So that'd be 69. Why am I at 11? Negative 11 meters. Is that right? Yep. Okay. I don't know why. I sometimes just get a little, I don't know what's going on. Okay. So let's look at this graphically too. There's another way you can do this. I can do this by finding, you'll notice that I'm talking right here, I have the average velocity times the time interval. So this is the average velocity. I'm sorry. This is the average velocity. That's 10. And that's the time interval of, what was it? 8. And 8 times 10 is this area. And I get 80. And then right here, I can also find the area right here. This is a triangle. So this goes from, now it's a little bit more difficult, and we can find this right here, but I don't know that I want to do that right now. When it stops, I will talk about how that corresponds graphically. So then I could find this area, 1/2 base times height, and then I could do the same thing for this part right here, 1/2 base times the height. But in this case, since the velocity is negative, this is a negative area. But if I find the area of this whole thing, I would get negative 3. Okay. So because I have I have a positive area and it doesn't even look like it's negative 3, but I'm going to trust that it is. Okay, well, I did find negative 3. And then I can find this area, it's going to be a negative value 2 by the area under the curve. Okay, so I got a total change in position of negative 11 meters. So this is the exact same program, and I printed out the position versus time graph, and this is what it looks like. Notice right here, I started at negative 30 meters. This doesn't tell you what x is. I'd have no idea. Okay, but in this case, I started at negative 30. I'm increasing with the constant velocity until I'm increasing my position with the constant velocity up to here, and then I start slowing down. So this is a parabola. That's that time right there where it changes to negative velocity, and then here it's moving backwards with some negative velocity. And here's the final position of negative 19. Here's the initial position of negative 30, and the change in position is 11. Is 11. I said negative 11, didn't I? Negative. That's not negative 11. I did that wrong. That's 80. Yeah, positive. Okay. So there you go. So this slope right here corresponds to the slope of that line is delta x over delta t, which is the average velocity, and that gives me this part right here. This part has a constant slope for the acceleration. A is delta v over delta t. So the slope of this is acceleration. Right here, that would be a parabola. Or as you like, parabola. That works fine too if you want to call it a parabola. And then here we have a negative velocity, so the slope of this part is negative also. Okay. So there you go. Now look at right here, the slope of the line right here is actually 0. So this is actually where it stops. Now the numbers aren't perfect right here, but it's somewhere around 11. And if you look over here, this is around 11. See, something's not right. It didn't plot. These two, this point right there corresponds with that point right there, because they're both at 0 velocity. And there you go. That's a simple position versus time versus velocity versus time, and finding the displacement from a velocity versus time graph. I'll see you guys later.